This lecture is part of a series of lectures on category theory and will be about monoidal categories. So I'll start with a couple of examples to explain what these are. So let's start with the category of sets. This has a product. We can take a product of two sets and we can define monoids, which are like groups without an inverse. So a monoid has a map from A times A to itself, and it also has an identity element, which is a map from the set with one element to A, and these should be associative and the identity should behave like an identity. Or we can look at the category of abelian groups. Now this has a tensor product of two groups, A tensor B, and we can form rings which have a map from A tensor A to A, and there's also a sort of identity element of the ring which corresponds to homomorphism from the integers to A, and this should be associative and this should behave like an identity and so on. So a monoidal category is a sort of common generalization of these two examples. So the category should have some sort of bifunctor taking two objects A and B of the category to something, which I'm going to write as a tensor product sign, although it need not be a tensor product. It might be a product, for example, but I've got to write it as something. And we also want some sort of object playing the role of the identity element. And since I used the tensor product from abelian groups, I'm going to use the one from sets just to be fair. So it should have a bifunction. It should also have an object 1, which should behave a bit like a unit in some ways. And the idea is we want to define monoids in this category to be objects with a map from A tensor A to A and a map from the object 1 to A, and these should satisfy some rules making them associative and making this the identity. So the problem is what conditions on this operation do we need apart from it being a bifunctor? Well, let's have a first attempt. Let's say that it should be associative, so A tensor B tensor C should be equal to A tensor B tensor C, and we should also want one tensor A to be equal to A, and this should be equal to A tensor 1. Well, there's an obvious problem. This isn't actually true in most cases. For instance, in sets, the product of A, B and C is not actually the same as the product of A with the product of B and C. I mean, it's isomorphic to it, but if you look at the definition, it's actually a sort of slightly different set, and the same with tensor products. So this isn't actually going to work because this isn't true, but never mind. Let's sort of assume this for the moment. So with these definitions, we get something called a strict monoidal category. And although I've said this doesn't really work in general, there are actually some reasonable examples that satisfy this rather strict condition. Before giving the general definition of a monoidal category, let's just do the strict one. So the first example is any monoid can be turned into one. Here, the category has one element, just sort of corresponding to the monoid, and this makes the tensor product of this one element with itself obvious because there's only one thing it can be. And the morphisms are just elements of the monoid, and a monoid becomes a monoidal category in a not terribly interesting way. More interesting example is the category of finite ordinals with order-preserving maps as the morphisms. So the category has element 0, 1, 2, 3, 4 and so on. And we think of 0 as being the empty set, and 1 as being the set containing just 0, and 2 as being the set containing just 0 and 1, and so on. And the tensor product in the category will just be addition of ordinals. So for instance, 2 tensor 3 will be the ordinal 5, and 0 will be the identity element. Unfortunately, there's a bit of a clash of notation because I was calling the identity element 1, which doesn't work here. Now we want to define a monoid in a monoidal category as some object with a map from A, tensor A to A, and we can take the monoid in this case to be the element 1 with a map from 1 tensor 1 to 1. Now 1 tensor 1 is just 2, and there's an obvious map from 2 to 1 which just takes, in fact there's only one map from 2 to 1 which just takes both elements to there. You can see you get maps between the elements of this category. For instance, you know the object n is now just isomorphic to 1 tensor 1 tensor 1 tensor 1 n times, and if we've got a map from n, any order preserving map from n to n can be obtained from this map here. For instance, if we've got a map from say 3 elements to 3 elements doing this, so here's an order preserving map from 0, 1, 2 to 0, 1, 2, then if we take 1 tensor 1 tensor 1, we can map it to 1 tensor 1 tensor 1 in accordance with this. First of all, we use the product of the monoid to map 1 tensor 1 to 1, then we just map 1 to 1, and then we sort of map 0 to 1 using the identity of the monoids, and that gives us a map from 3 to 3 corresponding to a map between tensor products of monoids. In fact, using this you can see that this is actually a sort of a universal monoid. The element 1 is a universal monoid. If we have any strict monoidal category and a monoid in it, then you can find that then you can write down a fairly obvious map from this category to the strict monoidal category, taking this to the monoid. So this is a sort of universal example. This category of order preserving maps turns up rather a lot. It's called the simplex category, and it's very closely related to things like simplicial sets. I mean, a simplicial set is essentially a contravariant from this functor from this category to the category of sets. Another example is a category of functors. So let's fix a category C, and we'll define a new category whose objects are functors from C to C, and whose morphisms are just natural transformations of functors. As we saw earlier, the functors from any category to any other category form a category, with the morphisms being natural transformations. So here we're just taking C to be itself. And now we can define the tensor product of two objects. This is just going to be composition of functors. And since composition of functors is strictly associative, we actually get a strict monoidal category from it. And the monoids of this category are actually the things called monads in category theory, and I might have another lecture on monads a bit later. I think these are important enough to have an entire lecture about them. Well, anyway, those are strict monoidal categories. As I said, in general, we have the problem that A tensor B tensor C is not actually equal to A tensor B tensor C, but just isomorphic to it. So for a non-strict monoidal category, we need to be given an isomorphism or a natural transformation of functors. So that means an isomorphism from A tensor B tensor C to A tensor B, tensor C that's natural, that commutes with morphisms and so on. And we also need to be given isomorphisms A tensor 1 to A and 1 tensor A to A. Well, do we need anything else? I mean, for abelian groups, we could define this isomorphism by A tensor B tensor C. Obviously, it's obviously going to map to A tensor B tensor C. But why do we do that? Why don't we map A tensor B tensor C to say minus A tensor B tensor C? Is that going to give us a monoidal category? Well, it turns out there's a problem if you try and define the isomorphism like this. And the problem is an example of a coherence condition. For example, suppose we have A tensor B, tensor C, tensor D. And there are several things you can do with this using the isomorphism from a tensor product of three things to something else. So we could map this to A tensor B, tensor C, tensor D. So that's, here we've got 1, 2, 3 things, and we're switching the tensor product. But then we can map this to A tensor B, tensor C, tensor D. And this should be isomorphic to A tensor B, tensor C, tensor D. I hope I'm getting all this right. This is all a bit confusing. So, so we've got a sort of cycle of 5 isomorphisms between these, and we want these to be consistent. In other words, if you go round this pentagon, you should get back to where you started. And you notice if you map A tensor B tensor C to A tensor to minus A tensor B tensor C, this diagram is not consistent. Well, there are a whole lot of other coherence conditions. For example, we need coherence conditions involving the unit object. We want A tensor 1 tensor B, and that should map to A tensor B, but we could also map this to A tensor 1 tensor B and map this to A tensor B, and we could have a map from 1 tensor 1 to 1, and we could have 2 different ways of doing this. So this is a coherence condition involving a tensor product of 4 objects. And as you can imagine, there are even more complicated coherence conditions involving a tensor product of 5 objects and some huge diagram of different isomorphisms we can write down, and you can get bigger and bigger and more complicated diagrams. So it looks as if it's going to be an absolute nightmare trying to define all the coherence conditions of a monoidal category. Fortunately, we don't need this. MacLean showed that provided you prove these basic conditions, then all the other higher coherence conditions can be deduced from them. The main one is this pentagon axiom. There are also the ones involving the identity object are sort of rather less interesting and nearly always valid. So a monoidal category, it has some sort of tensor product. It has some isomorphisms from A tensor B tensor C to A tensor B tensor C, and it has to satisfy these coherence conditions, in particular the pentagon diagram. There are now lots of examples of this. We have sets with the usual product, and here the monoids in the category are going to be the usual monoids, or we can have abelian groups with the tensor product, and here the monoids are going to be rings. Or you can take categories and take the product of categories, and the monoids in this category turn out to be strict monoidal categories. So it's getting a bit recursive. You can define monoidal categories as monoids in a certain monoidal category, which is kind of confusing. Well, there's also a couple of extensions of this. We can also have things called symmetric monoidal categories. So the usual tensor product satisfies A tensor B is equal to B tensor A. Well, as we saw, it's not actually equal to B tensor A. A tensor B is isomorphic to B tensor A. And as we saw, we have to be careful to actually write down this isomorphism explicitly. For instance, we might map A tensor B to B tensor A. And if you've got this isomorphism, you can now use it to define things like commutative monoids and commutative rings, because if you want to define the monoid to be commutative, you say A tensor A, and then you, let's call this map T. So if you've got the sort of switch map from A tensor A to A tensor A, you want this diagram to be commutative and so on. So if you've got this extra structure, you can now define commutative objects. And we notice you don't always have this extra structure. For example, if your monoidal category is functors from a category to itself, and tensor product is composition, well, the composition of A and B has very little to do with the composition of B and A in general. So not all monoidal categories have a nice symmetric structure. Well, if you do this, you're obviously going to have some more coherence conditions. So let's just show what sort of coherence conditions you get. The main one you get is a sort of hexagon diagram. So we can sort of do this. We can map this to B tensor A tensor C, but we can also map this to B tensor A tensor C, and we can map this to B tensor C tensor A, and then we can map this to B tensor C tensor A, and we can map this to A tensor B tensor C. And you want this hexagon diagram to be commutative. In other words, if you start here and go round using all the isomorphisms you've defined, you want to get back to where you started. For instance, if we defined A tensor B to map to minus B tensor A, then you can see this diagram wouldn't commute, so this wouldn't be a very good way of defining the isomorphism from A tensor B to B tensor A. Of course, you should define A tensor B maps to B tensor A, and then everything works very nicely. And you also, for a symmetric category, you want things like if you map A tensor B to B tensor A, and then map that to A tensor B again, you want this to be the identity map. And if you do this, you find if you take a product of n things, then this is acted on by the symmetric group Sn. That's sort of why they're called symmetric tensor categories, that you get actions of the symmetric group on everything. Actually, there's a sort of interesting variation. If you want, you can actually drop this condition. And if you drop this condition, you get things called braided monoidal categories. And for braided monoidal categories, are called braided monoidal categories because you only have an action of the braid group on this, because if you switch these two things and then switch them back again, you don't get what you first started with. Anyway, I should give you a slightly not quite trivial example of a symmetric monoidal category. So let's take the category of abelian groups, and let's just have the usual tensor product of A and B as our making it into a monoidal category. And then we need an isomorphism from A tensor B tensor C to A tensor B tensor C, and this is going to map A tensor B tensor C to A tensor B tensor C. And we need an isomorphism from A tensor B to B tensor A, which is going to take A tensor B to B tensor A. And this is obvious and trivial, and you wonder why you even bother writing down something so obvious. Well, it turns out there's a sort of interesting variation you can do. As we've said, if you map A tensor B to minus B tensor A, this doesn't work. So let's cross it out. However, it almost works. There's a slight change you can make to this. Let's look at Z modulo 2Z graded abelian groups. So our abelian groups are going to be written as A0 plus A1, where so they're the sum of an even piece and an odd piece. And now I'm going to map a tensor b to -1 to the degree of a times the degree of b times b tensor a. So there are two different isomorphisms we can choose from a tensor b to b tensor a. So this one gives you the usual monoidal category of abelian groups. This one gives us sort of super objects. So commutative rings in this category are just the usual commutative rings. If we try doing commutative rings in this category, well, in order for rings to be commutative, we need to use the isomorphism a tensor b to b tensor a. And this is going to give us what are actually supercommutative rings, where they have the property that AB is equal to -1 to the degree of A times the degree of B times BA, wherever A and B are graded. We can also define in this category, we can also define a lot of other algebraic objects. For example, instead of rings, we can define Lie algebras, and Lie algebras in this category are usual Lie algebras. Lie algebras in this category turn out to be the so-called Lie superalgebras, which are sort of like Lie algebras, but they have sign errors in them. These were actually sort of discovered by physicists in about 1930, except they use different terminology because super mathematics hadn't really been invented at that time. The usual commutation relation of a Lie algebra gives us AB is AB minus BA. So whenever you have an expression like AB minus BA appearing, you're working with ordinary Lie algebras. And in quantum mechanics, you had things like a position operator and a momentum operator, which satisfy AB minus BA is equal to 1. When physicists started working with fermions, you discover you get creation and annihilation operators which satisfy AB plus BA equals 1. So this is like a commutator, except it's got a sign error. We're saying AB plus BA instead of AB minus BA. So this is actually AB minus -1 to the degree A times the degree of B times BA. So what we've actually got here is a sort of supercommutator of A and B. So what physicists were really doing was they were working inside this sort of twisted version of the category of abelian groups, where you have a funny change to the isomorphism between A tensor B and B tensor A. So this is just to illustrate that you really do sometimes need to pay attention to these isomorphisms between A tensor B and B tensor A. It might sound like a completely boring piece of bookkeeping, but it does sometimes make a real difference. I mean, the only difference between these two monoidal categories is they have different isomorphisms between A tensor B and B tensor A. Okay, that's enough about monoidal categories.